Well, welcome, Earth-Space Science class. My name is Brian Anderson, and you can call me Brian. You can call me Professor Anderson. Mr. Anderson doesn't matter. Brian is really just fine. I like to set a relaxed tone in this class, so whatever you're comfortable with, I'll be good with. Hopefully the webcam that's recording the little box that my face appears in down in the lower right-hand corner is not being too obscured by the light behind me. Anyway, I'm not going to go over the syllabus in this first lecture. I will do that on Thursday of the first week of class when we're meeting in person. I'm going to, as I mentioned, record the first two lectures online. My hope is to do about a 20 or 30-minute lecture for each of the first 2 days. And the reason is my wife's dad is not doing well. He was just put in hospice yesterday. My wife is actually an RN in St. John's on the COVID floor, so she's one of the frontline workers. As soon as we can, we're going to get down to Kansas and let her see her dad for what may be the last time. We don't know. We never know. That's why we are not going to be in class the first 2 days, and you'll have to suffer under a video lecture. Okay, so hopefully that's enough of an explanation for now. I can give you more on Thursday. So we're going to start off with a consideration of geologic time. And time is an issue that humanity has tried to track, marking significant events for as long as we know humanity was thinking about such things. And so they built structures. Now, this is an Earth space science class, so I have the dubious honor of handling two topics, geology and astronomy. I'm going to start out with a little bit of geology, astronomy mixed. We'll do the geology, and then we'll end up with the astronomy piece of this class. So here's a structure. This is Stonehenge, a little south and east of London, England. And this was built, as it says, 4,000 to 5,000 years ago. And the intent of it was to track calendrical events. If you look at it, there are these large stones, and certain alignments are made at certain times of the year with sunrise, sunset, certain bright stars, things of that sort. If I minimize this just a little bit and open up Google Earth, you'll see from a distance the true footprint of structures like Stonehenge. So we'll just do a little search for Stonehenge. And it will zoom us into that. Again, the southeast portion of England. There you can see it. Okay, that's a little southwest of London, my bad. So here, if we look at Stonehenge, this is the inner stone monument, but you can see there's an outer ring here as well. And there are what are called heel stones placed out from the stone that make for the alignments that people were interested in when Stonehenge was built. Another feature is something called the Bighorn Medicine Wheel. And this is in Wyoming, and this is what it looks like. It was constructed by Paleo Indians, when you look at the alignments, it's again looking at certain bright stars or sunrise or sunset at certain important times of the year, like the solstice, summer solstice, the day when the sun rises to the highest point in the sky, the longest day of the year, that sort of thing. Sirius is the brightest star in the night sky. Rigel, Formalhaut, these are all bright stars, Aldebaran, that were being tracked as a calendar by Paleo Indians in Wyoming. This is just outside of St. Louis, Missouri, is a place called Cahokia Mounds, and this is an area, a site that was active in the Mississippian culture, around 900 to 1300 AD. This is, as it says, about 1,000 years old. But in this site, similarly, there is evidences of what we call a wood henge. Posts that were placed strategically in the ground to track sunrise, sunset, moon positioning, bright star positioning, to track time. Okay. If you go to Mexico, this is Teotihuacan outside of Mexico City, or very near Mexico City. These are some of the largest pyramids in the world. They rival the pyramids in Egypt, the Great Pyramids in Egypt. And These aren't quite as old as those, but this is the Avenue of the Dead, the Pyramid of the Sun. All of these structures similarly were constructed to, among other things, track the time of the year. So biblically, time is also an important issue. If I was to ask you what a controversial issue in geology might be, it's kind of hard to think of a rock as being controversial. You know, look at this rock. Okay, here's a rock. Doesn't look very controversial. Kind of cool pattern in there. Might be controversial if I took that rock and threw it at somebody, but well, you know, what about geology is controversial? And certainly within the biblical realm, the issue of the age of the earth is something that people still disagree about. And I've had students recently in this class that have not agreed with various elements of it. Now, I want you to know in this class, you will never be denigrated, run down, graded poorly because you disagree with my position. My position is that the earth is old, that God made the earth and everything in it just as he said in the Bible, but that he did so a long time ago, realizing that I could be wrong. I wasn't there when he did it, despite my age, but the best evidence that we can look at from our senses, and I would argue also from the Bible, would support an older earth. But I realize you may not all agree with me, and that is just fine. You will not be graded down or anything for that. So when we consider the age of the earth, I like to tell a story. When I was a freshman in college in 1976, I was a freshman in college, and I went to St. Paul Bible College, now Crown College. I love the institution. That's the denomination I grew up in, the Christian Missionary Alliance. And there at Crown, like at Bethel, we were required to take certain Bible classes. There, at that time, it was OTH and NTH, Old Testament history and New Testament history. Old Testament history was taught by Dr. Olson. He was automatically cool because he drove a red Corvette. Anyway, when we went through the biblical account of creation, and I'll just read the first couple of verses, it says, "In the beginning, God created the heavens and the earth. Now the earth was formless and empty. Darkness was over the surface of the deep, and the Spirit of God was hovering over the waters. And God said, 'Let there be light,' and there was light. God saw that the light was good, and he separated the light from the darkness. God called the light day, and the darkness he called night. And there was evening, and there was morning the first day." And so on and so forth through the whole creation account. Well, Dr. Olson talked about the fact that there were at least 20 different positions that various people took on interpreting the creation account, all under the umbrella of orthodoxy. Now, by orthodoxy, I mean everybody with a different position could disagree with one another, but at the end of the day, they all thought they were going to heaven because they agreed on the important things scripturally. The gospel message, that Jesus Christ is God's Son, that he came to earth, died for our sins, rose on the third day, and lives now and can live in our hearts if we invite him in. That's the gospel issue. We all have to agree on that, or we need to seriously consider what the Bible says and our position on these matters. I would argue that that's a central issue. So that's a gospel issue. That's a central issue. The age of the earth is more of a peripheral issue. It's not going to determine where we spend eternity. But we can talk about it, we can argue about it, we can disagree on it, and that's fine. I think a consideration of it allows us to see God's working in creation, and I think it's a good thing to think about. Even if you're a person that thinks the earth is quite young, it's good for you to know what the position of one who thinks it's quite old is, and vice versa. So Dr. Olson talked about 4 different positions people could take, and you see them listed there in your notes. The first is a literal day theory, and a literal day theorist thinks that the Genesis account refers to 24-hour periods of time, each of those days in the Genesis account, and that creation took about 6 days to happen, that it all occurred in about 4004 BC. The church actually hired Archbishop Usher and Sir John Lightfoot, I think two different people, to go back using the genealogies and try to figure out when the earth was actually created. And they actually thought it was somewhere around 9 in the evening, September, October, something like that. I'm not sure how they came to those numbers, but somewhere around 4,000, a little more than that BC. Okay, so that's a literal day perspective on the meaning of the Genesis account. An age day theorist would argue that there are passages in the Bible that say a day is to the Lord as 1,000 years and 1,000 years is a day. The idea that a day to God is not viewed the same as a day for us. And so that when the Genesis account talks about days, they're not a literal 24-hour period, but a longer, less defined period of time. It's kind of like in the day of President Trump, certain things happened. So that would be how we would use that word day, a longer, less defined period of time. You actually might know that Hebrew word. It is yom, and it does translate very nicely into English because our word day can be used similarly. If you've hung around the Bible theology department for your Intro to Bible class, you may have heard of the gap theory, or if you have not yet, you may in the future. Gap theorist says that when you look at passages in the creation account, for instance, Genesis 1:1, in the beginning God created the heavens and the earth. Now the earth was formless and empty, and darkness was over the deep, and so on and so forth. And then you go to verse 3, it says, God said, let there be light, and there was light. There's a transformation in the language there. The first verse uses language that really looks like a battlefield, a place of destruction, if you will, would be similar. Use similar language that we see in verse 1, and then following that we see and 1 and 2, and following that we see a change in the verbiage used. And so a gap theorist says that's a big gap that occurred right there. Something happened. Maybe that's when Satan was thrown out of heaven with the third of his angels and hits earth in big cataclysm. Maybe that's when an asteroid hit the Yucatan Peninsula and made a big cataclysm, whatever. There was big destruction and a big change occurred, a gap of time, if you will. That's what a gap theorist would think. The last one is a revelation day. And if you think about who wrote the book of Genesis, it was Moses. Or at least that's what we believe. Now, Moses was not there to view creation, so this had to be given to him as a revelation for him to write the book of Genesis. And so a Revelation Day theorist would say, we don't understand this book of Genesis like we should. It should more correctly be read. On the first day of God's revelation to Moses, he told Moses that he created the heavens and the earth. On the second day of God's revelation to Moses, and so you see, each day referenced in the Genesis account is not referring to a day of creation, rather a day of revelation. Now you got to understand, I am not doing justice to these. I'm just giving you a thumbnail sketch of them, and just a representation, if you will. Somebody that was a proponent of each of these would do a much better job than I'm doing. I want to show you a picture here now of a spot in England, and maybe we'll look at that spot if I can find it. It's called Sycamore Point, Cockburnspath, UK. So this is southeastern Scotland, where we're going to. And, I think it was in the 1700s, a person by the name of Sir John Hutton was in this area. And if we look at this area, I'll zoom in quite a bit more here just for kicks and grins. And it's kind of a unique area. You say, well, that looks kind of non-distinct. I mean, yeah, it's a piece of the southeast Scottish coast. Well, if we go to that spot and we actually look at it, this is what you would see. Now, Hutton went to this spot and he looked at it, and you can see layers of rock here, then vertical layers of rock here. And these rocks are sandstone. Okay, these red sandstone here. And sandstone is made as pieces of other rock somewhere else gets weathered. Weathering forces chiseling pieces of sand-sized pieces off. Those sand-sized pieces had to have been then moved from their source, from the place they were weathered, from the rock they were weathered from, to this location right here, deposited, lithified, in other words, formed into this rock. Time had to pass, and then this rock was obviously displaced because it's no longer horizontal, and it itself has been weathering. And it said that when Hutton looked at a piece of sand that fell off this rock right here and thought about all that went on before that piece of sand got to this spot, was part of another rock somewhere else, and all that had to go on to cause that particle of sand to be weathered off this sandstone and roll along the beach. It said he was looking so far back into the span of time that he couldn't conceive of a beginning nor an end to it. It was just a consideration of infinity, if you will. And so this is what it's believed is going on at that spot. This is a 345 million year old sedimentary rock that was actually deposited in a desert, and now it's a beach. When we get a little farther along, I'll explain, give you some ideas of how people would have such an idea about such things. And unconformity means there was a period of time when there was no rock on top of this rock here. And we don't know much about it because that information is gone. And then down here are these vertical sedimentary rocks that are believed to be 425 million years old. And so you think about the span of time that had to go into that. It was just, how can we ever think to know anything about it? Well, if you look in your notes, the principle of uniformitarianism says that these laws that govern our world today are the same as those that govern the world when these rocks were deposited. And so, if you think about, for instance, so some people will have real problems with this law of uniformitarianism. They'll say that, well, if you look at the Mississippi River, for instance, there's good evidence that it doesn't flow today at the same rate it flowed a long time ago. It used to flow at a much higher rate, probably when glacial meltwater was filling it. But now it flows significantly at a significantly slower rate. So that disproves uniformitarianism. There's no uniform flow rate in the Mississippi. Well, uniformitarianism does not say that. It does not say that the Mississippi River had to flow at the same rate. It says it has to flow for the same reason. Well, if you think about why does a river flow, because water is obeying gravity, the law of gravity. There is a biblical parallel to this too, a biblical reinforcement, I should say, of this. And so if we go to Jeremiah, was it 26, 25, and 26? Here, Jeremiah is saying, this is what the Lord says. If I have not established my covenant with day and night and the fixed laws of heaven and earth, then I will reject the descendants of Jacob. So he's talking about the fixed laws of heaven and earth. So if the laws that dictated Earth's being, Earth's existence, a long time ago when these rocks were formed, are the same as the laws that are dictating the Earth's existence today, then we can use that information to investigate what went on to make these rocks a long, long time ago. That's uniformitarianism. The past is the key. The present is the key to the past. It's is oftentimes referenced. Okay, so some things we look at then when it comes to geologic time. Geologic time, again, from an old Earth perspective, is much much longer than humans think of. So this is 4.5 billion years. Over that, it's believed the Earth was around from an old Earth perspective. And so if you look at just this Phanerozoic period, Precambrian, That's named after rocks of that age that were found in the Cambrian region of England. So any rocks that were older than those are called Precambrian rocks. That's where that name comes from. Cenozoic, Mesozoic, Paleozoic. Zoic is life. So ancient life, paleo, ancient, meso, middle, ceno, recent. And so all these terms have meaning. Here's some terms that maybe are more familiar. Jurassic, like Jurassic Park. And so Triassic, Jurassic, Cretaceous. This is a look at that geologic timeline and some of the divisions of it that have occurred down through time. When we go to Taylor's Falls on our field trip, we're going to be looking at some rocks that, well, they're getting pretty old. If we look at a different timeline here, show up here. It's a little bit hard to see. But we're going to be looking at rocks that were formed in this era 400, 500 million years ago, again, believed from an old Earth perspective. You'll actually be holding a rock that was formed at that time. Okay, so when we think about geologic time, it's broken up into two parts, absolute and relative. And I always have a little fun with this. We used to call it absolute dating techniques and relative dating techniques. But then relative dating is rather frowned upon at Bethel, so we call it relative time. So yeah, that's my attempt at humor. Okay, so geologic time. If you think about absolute time, that's would be like me asking you what your age is and how old are you? You're 18, you're 19, you're 20, you're 21, you're 22, whatever you are. You'd be giving me a date in absolute time, in absolute number of years. If I ask this rock how old it is, well, A, rocks don't talk, at least not that I know, and B, it would be a very, very old rock. And so how can we tell how old the rock is, or some inanimate object, given the fact that it can't talk to us and tell us? Well, we use the concept of uniformitarianism, the idea that the laws that acted on Earth when that rock was made are acting on it now, and we apply those and we see if we can get some clues. One of the things we can look at is something called radiometric dating. So you probably have heard of carbon dating. So here I have a toe bone from a Pleistocene horse, Ice Age horse, if you will. This came from Kansas. My wife is from western Kansas, and so this was found there and given to us. So here's another piece of that. And also, I thought this is kind of interesting. Here's a piece of the hoof. And I should hold it the right way. Okay. How can we know how old that bone is? Well, we could use radiometric dating, and it goes like this. When you look at this bone, when this horse was alive, I'll hold a piece of a hoof up because it looks kind of like a hoof. When this horse was alive, it was taking in carbon when it was eating, and it did so its whole life. And most of the carbon that it took in was what we call carbon-12. The 12 means it had 6 protons and 6 neutrons. 12, okay? And almost all the carbon in all the world is carbon-12. But every so often, rarely, you get a carbon with an additional neutron. That's carbon-13, but that's stable. Even more rarely, you get a carbon with 2 additional neutrons. That's carbon-14. That one is unstable. It breaks down over time into nitrogen-14. So if I take this bone, this horse's hoof, and I look at it and I see how much carbon-14 is in it, and compare that to how much nitrogen-14 is in it, I can get an idea for how old this bone is. Because you see, if there's a lot of nitrogen-14, that tells me that a lot of time has transpired to allow the carbon-14 to convert to nitrogen-14. Conversely, if it's got a lot of carbon-14 and not much nitrogen-14, it would seem young then, because not enough time has transpired to allow that carbon-14 to convert to nitrogen-14. Okay, we call that radiometric dating, and the amount of time it takes for half of that carbon-14 in this analogy to break down into nitrogen-14 would be called a half-life. Okay, so one half-life would be the time it takes for half of the carbon-14 that was in this bone originally to break down to nitrogen-14. So you'd have a half that's carbon-14, a half that's nitrogen-14. Of that half that's still carbon-14, You would then look at how much time it took for half of the remaining to break down into nitrogen-14, and that would be a second half-life, and so on and so forth, until you have such a infinitesimally small amount of carbon-14 that you can no longer really measure it well. So carbon-14, usually it's effective to 40, 50,000 years. You can extend it to maybe 100,000 years with new techniques, but beyond that, there's just not enough carbon-14 around any longer to measure it. Other isotopes, other atoms break down much more slowly, like potassium to argon, and a form of potassium to a form of argon. And so it would allow us to extend our information back in time a lot farther. And that's what we would use on a rock. Carbon dating is only good on things that used to be alive. But potassium argon and other types of dating are good on inanimate objects like rocks. There's another type of a structure called a varve. Let's see, I think I want to go here. Yeah. This is an ice varve, and these are layers of ice that are laid down, one layer per year, okay? Typically you have a snowy season and a dry season that allows a line of distinction to be made between each layer. And you can actually count back tens and hundreds of thousands of years in ice cores. I've heard that there's one spot on the edge of Antarctica that you can get a 2 million year old ice core from. I haven't verified that, but you can definitely go back counting rings of ice back 100,000 years. This rather pleased with himself looking gentleman here is showing you a lake bottom, and I think it's in Nigeria. Might be wrong on that. It's in Africa somewhere. But there are varves here as annual layers of sediment were deposited in this old dry lake bed. And again, we can count an actual number and find out how old those varves were. And each of those varves and each of those ice cores, there's information contained. There's pollen grains. There's atmospheric gas bubbles that tell us what the atmosphere was like, what things were living at that time. So little bits of information are contained in varves. And this rock that I held up, this is called varved shale. And I should hold it upright here. Back it up a little bit. There we go. And you can see each of these layers, actually, it's believed a dark layer was formed as organic sediment was deposited in a glacial lake in the summertime. The lighter layers were formed as the glacier created rock flour, this fine rock flour that was then deposited on top of the organic sediment in wintertime, so that one dark and one light layer would represent 1 year. Now, of course, this rock was taken from a larger mass of a rock, but in that bigger rock, you could count back then physically in time and establish an absolute age on things. And so those are varves. Lastly is dendrochronology. This would be the activity that we would start the class off with. I want you to go to a website, and it is linked in Moodle, and it should look, well, there, like this. This young lady is a PhD at Kansas. I don't know if it's Kansas State or KU. That's a big deal if you're in Kansas. She is going to explain dendrochronology, basically tree ring dating. And so I want you to just pause right now this video, go take a look at that, and then come back. Now, you're going to be elementary education teachers, and so what the lady in the video is going to show you is something called an increment borer. Now, you're not going to have access to an increment borer likely, although every school district, there will be a county, there's a county forester, and you might be able to get your hands on one. But you can just take a piece of firewood, cut some pieces off, oak is really good, sand them up, and you can still use that concept to date the age of a tree. In an elementary class, kids can count rings. And so that will work pretty well. Okay, so those are all ways, radiometric dating, varves, and dendrochronology, of establishing geologic time and absolute time. We're going to shift gears here for a second now, and we're going to look at some ways of establishing relative time. So in our class, there will be some of you that might be 18 years old, some of you that are 19 years old, some of you that are 20 years old. I'm 62 years old. So you know, we could say, without asking you your age, if there was one of you that was younger, I would say that the whole student body likely is younger than I am. Now, in that statement, I haven't aged any of you or myself, saying I am older than all of my students. Okay, that would be placing us in a chronological order. I am older, you are younger. And that would be an example of relative dating, just placing things in chronological order without necessarily establishing the age of them, of any one. So there are some principles that might seem so obvious that, you know, why are we even talking about them? I'll use this diagram to represent them. So here are some layers of rock. It gives them some names that probably don't mean much right now, but will later. Here's a shale, here's a conglomerate, here's a sandstone. Okay, these are all types of sedimentary rocks. But just, you don't need to know the names of them, but you can see there's obviously layers of them here. Okay. And the first principle here says the principle of original horizontality. For instance, this sandstone here is made of particles of sand that have been lithified or squeezed or glued together into a stone. Okay, this first principle would say this layer of sandstone had to be deposited in a horizontal manner. Okay, the sediment was laid down horizontally. In other words, it was laid down like this. There was no pinnacles, no columns of sand that were created. It was laid down horizontally. And I'd say, duh, of course, that's how sand gets laid down. It gets laid down in a horizontal fashion. Well, if that's so, then how do I explain that picture? Hopefully it's not too dark for you. Here there are obviously layers of rock that are not horizontal. Well, the answer is that movement within the Earth's crust has deformed that rock, has changed its shape. So like this sheet of paper would represent the original layer of rock that was formed as the sediment was deposited horizontally, okay? But then because of movements within the crust, it got wrinkled like this. And now we see in this road cut, those wrinkles exposed. I'm pointing to the screen like you can see that. Those wrinkles exposed here, and now they're no longer obviously horizontal, okay? If we go to another one here, we can see the extreme where in this Idaho phosphate mine, some of these layers are actually tipped over backwards. Wow, look at that. So extreme plate motion. But these are obviously disturbed rocks. And so in the principle of original horizontality, we're still going to make the assumption that all sediment, no matter what happened to it afterwards, all sediment was initially laid down horizontally. Okay. Number two, principle of superposition. If you look here, this sandstone was laid down first, and then this layer on top, and then this conglomerate, and then another layer, and then a shale. And so the assumption would be that this sandstone must be older than this conglomerate, which is on top of it, or the shale, which is on top of it. And again, that's very common sense, unless you consider the rare occurrences where you actually do have rock layers that are turned over. Now this one down here would be older than, or would be younger than this one up here, because the layers were originally, in this orientation, they were originally flat, horizontal, and got tipped up and over and inverted. But this is a rare situation, not common. Most of the time, this is the case. And if this is the case, if this, in your notes, it says in an undisturbed rock sequence. So this would be, oops, and where did you go? This would be a disturbed rock sequence, okay? This would be an undisturbed rock sequence, and this is most common. Okay, what they're also showing here, number 3, is a principle of cross-cutting right here. And in this particular example, this rock existed, but then this magma burned its way across, melted its way through the rock, and then cooled. We would call that structure a dike. Now, if you look at what those look like in actuality, let's see here, I think, oops. Maybe I've got a picture of one. Not there. Where did you go? Here's one. Okay. This is a picture, I think this is in northern Minnesota or southern Ontario, but there is obviously a layer of rock that's burned its way across that previously existing layer. And so this principle number 3 would say that this dike, this cross-cutting cooled body of lava must be younger than the rock that it cross-cut. In other words, this rock here had to have existed before and therefore be older than this magma that has cut across it. I think I've got another one here. Is it this one? No. I wanted to, it's a scroll down one that I wanted to look at, so we'll look here. Yeah, this is it. Maybe a better example, as you can obviously see layers of sedimentary rock here, and then the magma that has burned its way across them and is now hardened. So this layer of magma, of cooled magma, must be younger than this rock around it. The last one is the principle of faunal succession or fossil succession. And so I have here a rock, and I'm hoping you can see this one, and it's got a little what we call a trilobite in it. Okay, and the principle of fossil succession or faunal succession would suggest that we can date the age of rocks like this one based on the age of the fossils in it if we know them. Okay, and well, that's good. Okay, but you know, there's some important considerations. Somebody's got to do the work of figuring out how old that fossil is, and so then be able to use that information to figure out how old the rock is. Now, there's certain fossils that are better, fossils that are abundantly preserved. So if I did a lot of work to figure out how old that little fossil was, and therefore then use that to assume how old this rock was, but then never found any fossils of that sort anywhere else ever on the whole earth, you might argue that was a waste of time, or wasn't of as much value anyway, because I can't use that then to date any other rock that I might find that fossil in, because I don't find any more of those fossils. It's helpful if the fossils are easily recognizable, okay? And so this is an easily recognizable fossil. There are many genuses of them, and so we could get particular and specific with that, so that's helpful. It's helpful, as it says in C, is if they existed for a relatively short period of time before they went extinct. So in other words, this fossil was created, and it existed for just a few thousand years, and then it went extinct. That would give us a good deal of specific information about the age of this rock then, if that fossil didn't live real long. For contrast's sake, what if I found this shark tooth in a rock? You know, would that be a good index fossil? Probably not, because sharks are still around, and so that it would tell us, yeah, you found a shark fossil, but it won't tell us any real information about how old the rock that it was in actually was. Now, in all honesty, this is a megalodon tooth. This is an extinct shark, so maybe that wasn't the best example, but the idea of shark's teeth not being real great. Alligator bones, crocodile bones, you know, not real helpful because they're still around and they've lived on Earth a long time. Okay, the last two have asterisks by them, and I'll explain that another time. But it's helpful if they're widespread geographically. In other words, if we find them in lots of places, so that we can use them to identify rocks in lots of places, but to age rocks in lots of places. And it's helpful if they couldn't swim or fly. So again, there will be more on that as we get into plate tectonics a little bit more. I'm going to finish right there, and yeah. And have a good day.